Okay, thank you very much for coming. Let me get right into it. So what does math have to do with golf? Well, probably in this audience there's a lot of people who wouldn't ask that question, wouldn't have difficulty imagining it. People like me who, after many years as a mathematician, an applied mathematician, a computational mathematician, I see math everywhere. Almost everything I look at, I take maybe this reductionist viewpoint that, well, you could model the key features in this way or that way, and you could do some reasoning and get some key insights of it. And from that point of view, golf is just one more example. There's many things that I could have talked about. So why did I talk about golf? Well, actually, I was approached by a public relations firm a few years ago. They had been hired by ExxonMobil that was producing a series of television public service ads, and the theme was math and science are everywhere. They were opening something called the Teachers' Academies. And I thought, well, that's a great theme. I'm happy to help. And they hired me as a consultant to put some of the math into the ads. In particular, one of the ones was going to be shown during the Masters Golf Tournament in Augusta, Georgia. This is close to as big an advertising spot as the Super Bowl. This is a big deal. And I'll show you the short version of that spot. And so it was Phil Mickelson, who was a big supporter of these Teachers' Academies, who was taking a golf swing, and my job was to find the math behind the golf, put it into equations that would look good, and help them work them into the ad. So I started doing a lot of research. There's lots of math in golf and all sorts of it, and I've just selected out 3 of the many things we could have talked about. The first, the swing, and then the impact, and then the flight of the ball. And really the main takeaway message is this paradigm of thinking about things where some system, say a real physical process, but it doesn't have to be, it could be a social process or something else, gets modeled by a mathematical model, which is something between a science and an art, and then that mathematical model is analyzed with all the many tools of mathematics, or simulated on a computer to get insight and understanding and eventually prediction and control. So the golf swing, from the moment you start bringing that club down to it hits the ball, that's all of a quarter of a second, and that's the only time the golfer has anything to do with the golf game. After that, the ball's on its own. But they have to control that very carefully. And when it's done well by somebody like Phil Mickelson, they have an acceleration from 0 to 120 mph in a quarter of a second. So take that Ferrari, that's 20 Gs. And let me look first at this ad. So you see the equations running by. I worked on every one of those very carefully.
Everywhere. That's why, along with ExxonMobil, my wife Amy and I created the Math and Science Teachers Academy, where elementary school teachers can learn new ways to inspire their students. Because if kids learn math and science, they can achieve almost anything. I'm Phil Mickelson, and I'm proud to work with ExxonMobil.
So as part of doing that, they provided me with a video so I could analyze the swing. And this is interesting for a golfer. Watch carefully what a real golfer's swing is. Notice how the arms are rather straight, and of course the golf club is straight. The angle between them changes so that they're almost in perfect alignment at the moment of impact. Let's watch that again. And imagine we want to model this rather complicated behavior. Well, let's start by sort of focusing in on what's essential in this. So here's a sort of very simplified sketch of it. And the key thing is the arms are kept rather rigid. And so what really matters is not this triangle formed by the 2 arms and the shoulders, but you could represent it pretty well by just a straight line from the center of the shoulders to the wrists. Then at the wrists there's a real pivoting, and then there's the straight line out to the club head where there's a mass. So those components, 2 pivots, 2 straight connecting lines, and a mass, are basically the system. The state of the system is described by 2 variables that vary in time, 2 angles, theta and phi. And the control that Phil has can be described by 2 functions, the torque he puts on with his shoulders and the torque he puts on with his wrists. That's these taus here, which he can vary in time. And of course the goal is to get it so this thing is moving very fast when it hits the ball. So you can write down differential equations of that using either Lagrangian mechanics or Newtonian mechanics. And so you have the system variables theta and phi, the angular velocities and rotations, the phi dots and phi double dots. A, B, and C would take into account the distances and the masses would be the right coefficients, and the torques here. So this is a little bit more complicated than the simple pendulum equation with one angle, which we know very well, and that one can be solved exactly. This one you can't solve it analytically, but you can either study it through dynamical systems or simulate it and solve it very accurately on a computer. One of the interesting facts is, although a single pendulum equation gives you about the simplest, most predictable system you can imagine. We know exactly what it's going to do, and that's why it was used to be the method of timekeeping for several centuries. It was about the most predictable thing on the planet. That's why they used it for timekeeping, at least in those time scales. As soon as you get two of them, it's not true. A double pendulum is a much more complicated object. Here's one of them. So imagine if this was a pendulum and I let it go, you know what it would do. So now it's a double pendulum. Suppose I let it go. Try to imagine ahead of time what it's going to do. Can you imagine? I'll just drop it, nothing else. See if this is what you imagined. So a double pendulum is a very complicated dynamical system, which is part of the reason why it's not so easy to do exactly the right thing. It's very sensitive to what you do. Part of the reason golf is so difficult. Did you think it was going to reverse at this point? Now, of course, most of the regime we're looking at has nothing to do with golf, which is only interested in the first half a stroke. Once it hits, then what it does is not too important. However, the goal is for a golfer to get it so that this angle and this angle are both accelerating at the same time reaching their highest velocity at the point where they're lined up and hit the ball. And you can get various insights by studying these equations. For instance, you find that the torque on the wrist is really of no importance. Your wrist should be basically a loose fulcrum. All the force is imparted with your shoulders. So what I bring this up for is give you a simple idea of the process of mathematical modeling and then analysis and computation. Of course, this model is not correct. We've skipped all sorts of things. It's really not true if you look very carefully at that video that the middle of Mickelson's shoulders don't move, that they're a fixed pivot. They move a little bit and so forth. And you can try to add further things into it. Let's see, I have here. So here's some of the things that people put in. In fact, adding that one refinement, allowing the top pivot to move, gets a little bit somewhat more complicated model, and that's considered very useful for teaching golf. There's this guy Jorgensen who wrote a book that still some people swear by as a way to learn golf, as a double pendulum with a moving fulcrum. But other people bring into account the fact that it's not really a two-dimensional pendulum, but has some three-dimensional aspects. You can study the effect of the fact that the shafts are not absolutely riveted, but bend, and so forth and so on. Before I do that, I'll go to those two slides I skipped. It's just showing some other uses of double pendulums, because they have this ability to generate these huge velocities. This is a kind of catapult, a trebuchet. Was used for biological warfare. They put diseased corpses in here, and you could get them over the walls and into the city you were trying to attack by this thing. And a slightly more complicated thing is what you could view a whip as a multi-pendulum. You have these two fulcrums where you can apply torque, and you can think of this as sort of a many-pieced pendulum. And the thing is, by applying the right torque, you can control it so you can accelerate that final point up to the speed of sound, which is how you crack a whip. So this is well summed up by this quote from George Box. A key point of mathematical models is they are wrong. Even if you could make a mathematical model that took into account every detail of the system that you're trying to do, then it wouldn't be much better. Simulating that and watching on the computer, if you did it right, would be like going out and watching Phil Mickelson hit a golf stroke. You wouldn't know how the hell he did it. right? So what you want to do is you want to find what are the key parameters that allow you to draw some insight. So all models are wrong, but some are useful. These are some of the things that the double pendulum model is used for. I'll just skip through this. So that's the first quarter of a second of a golf game, and as I say, that's the one where the golfer is involved. The next part, the laws of physics take over completely, so we won't have any inputs to these, like those torques, which is the transfer of momentum from the club to the ball. So what we're talking about, and this is a still from the public service ad with, this is my favorite of the equations I put in, because the notation was tried to put in there, so even if you don't know much math, you sort of get that math is telling you about things like the speed of a ball and in terms of the mass of the ball and so forth. So what we're talking about is how momentum is transferred from this club head that we got up to 120 miles an hour to the ball, and how fast does the ball travel when it leaves the club head. Here's what's going on. This is happening in 1/2000th of a second. The club head is coming into contact with the ball, and the ball is being deformed. So it gets, you can think of the ball as a very, very compressed spring. It's a very rigid spring, and it's been compressed really far from its point of view, and then therefore it expands out and pushes back against the club and returns to spherical, and as it does that, it picks up a lot of momentum. So how fast does it go? Well, so this can be modeled using Newtonian mechanics. The key concepts are momentum and velocity. Momentum is the mass of, say, the club head times its velocity, or the mass of the ball times its velocity, and kinetic energy is 1/2 mass velocity squared. And we have conservation of momentum. So we have the momentum of the club before, V club is the velocity before contact, is the momentum of the club after, capital V club is the velocity after contact, plus whatever momentum was transferred to the ball. And something similar for kinetic energy. And then what tools do we need to analyze this model? Well, before we needed differential equations. Here we need high school algebra. This is 2 equations, and we have 2 unknowns, the velocity afterwards of the club and the ball. So we solve our 2 equations and 2 unknowns, and we get these nice formulas. So what do we learn from these formulas? Well, everything depends on the ratio of the mass of the club to the mass of the ball. For example, if you take one of these machines that you can buy in an office toy store, the mass of one ball is the mass of the next ball, and so this is 0, which says that the ball coming in will end up with 0 speed, which is what happens. The ball comes in and it stops. The ball going out, according to this, will end up with 2 over 1 plus, well, this ratio is 1, 2 over 2 times the ball of the club, so the ball going out will go out with the same velocity, and you'll get that picture you've seen. I'm sure you've seen these things, right? They go like this. So that's simple Newtonian mechanics. I find this a nice formula because it tells you no matter what you do, no matter how you design your golf clubs and stuff, that ball is not going out any faster than twice the speed of the club. And if you want to go twice the speed of the club has to weigh infinity, right? You'll be less than twice the speed of the club. If you drop a ping pong ball in front of a moving freight train and there's no air resistance, the ball will go off at twice the speed of the freight train, no more. So there's the formula again, and if we apply this where we put it in the mass ratio for a standard golf club and a ball, remember the club head was going 120 miles an hour, so the ball will go off at 195 miles per hour. Unfortunately, that's not really true. Very few people can get a ball up. I'm not sure anybody can hit 195. So what's wrong with it? Well, it's an insightful model, it's a useful one, but it's not sufficiently accurate. If you're really trying to predict speed from it, you've cut away too much out of your model. So the reason is, conservation of momentum is fine, but conservation of energy, the law is conservation of energy. The law is not conservation of kinetic energy, which is all I computed. There's other kind of energy. When you smash a ball and make it that shape, you do damage to the atomic bonds inside that ball, you create heat and friction. All that's energy that's sucked away from the kinetic energy. So now you could try to model that. Well, You could go down to the level of the atomic bonds and try to do a very complex model that way. That would be very difficult. The most common way of modeling that is to do a couple of measurements of the ball and sum it all up in one number, the coefficient of restitution, that measures to what extent it actually transfers the full kinetic energy. CR equals 1 would get us back to the model where we were, but for a real interaction between two objects, the coefficient of restitution will be somewhat less than 1. That's why when you drop a basketball, it doesn't keep bouncing up to the same height, because the coefficient of restitution and the contact between the floor and the ball is less than 1. So for a golf ball, golf club, it's about 0.78, and that's something the manufacturers can fiddle around with. So when you pay more and more money for your better and better golf clubs, they're trying to adjust that parameter upwards. With a CR of 0.78, you'll end up with a ball speed of about 175 miles an hour.
You might be getting to that, but does that coefficient of restitution include like the spring force? Because you're not
yes.
compressing it, it also is.
So it's really one imperfect spring hitting another imperfect spring, where both of these springs have very large spring constants. They don't like compressing at all. The club really, but the club itself compresses. And there are people who have been made golf clubs that actually have springs in them, so that the club face moves in and bounces back. They're illegal, I think. But one of the things about this, when I did all this stuff, I thought, wow, now I know this. I could optimize this and come up with like the best club and the best ball and make a fortune. And then I found out how they test what was allowed. What they do is they go back to one of those robots that uses a double pendulum. You give them your new ball or your new club that you designed. They have the robot hit it. If it goes too far, they say that's not allowed. So now we get to the flight. So now what we have is, based on the two previous steps, we're in a situation where we know how fast the ball is going to go and in what direction the ball is going to go. Actually, it's very important the angle that you hit it in, so the direction, and also there's a little bit of a vertical motion when you hit it, so it causes a spin. But let's just talk about the ball going off at a certain speed in a certain direction. So now the question is, how far does it go? And what's its trajectory? So many people in this room have taught calculus one time or another, and they've all given this question in numerous disguises to their students. They've given an initial velocity and initial direction of this. How far did it go? How high did it go? How far was it aloft? How much time was up versus down, et cetera, et cetera, et cetera. And this is generally the way to solve a problem like that. So you take your velocity vector, so your speed and your direction. You break it into two components. One is horizontal, one is vertical. In the horizontal direction, you say it follows Newton's law. It'll keep moving at the same speed in the same direction because there's no forces acting on it horizontally. So x is just a multiple of t. And in the y direction, there is a force acting, gravity. Golf would be a very different game if there were no gravity. And that causes this to go quadratically in time, and so when you plot this versus this, you get a parabola, a downward pointing, convex down parabola. And then you can easily figure out all these questions and pass your calculus test. So let's hold that mathematical model, and again here the analysis was basic calculus or even algebra. Let's hold that up to a test against reality. Let's see if I can get the video to work this time. So let me mention a couple of things here. This is Phil Mickelson again. This is at the Buick Invitational at Torrey Pines. They have a sensing technology that follows the ball and draws a path, so you can see it started here and headed up. He's aiming for the flag, which is over there. It's 430 yards away, I believe. Good long distance. You can barely see it. And the first thing we see is this is nothing like a convex down parabola, which would be something like this. Its highest point should be halfway. Well, but I'll let you see it. And by the way, it's remarkably close to that flag. That's a good drive. But you compare this to this, they seem to have nothing to do with each other. So what's wrong? Well, we calculus teachers are off the hook because we all have fine print in our questions. It all says, ignoring air resistance, find the trajectory of a ball. So we ignore air resistance, our students ignore air resistance, but the golf ball does not ignore air resistance. So in order to make a useful model out of this, some models are useful, but this one is not at all for predicting the trajectory of a ball. We have to take into account the force of the air on the ball. So that turns out not to be so simple, and now we get to much more complicated mathematical models. The first thing we do is, like we did with the velocity, we decompose it into two orthogonal directions. But instead of horizontal and vertical, it's very useful to take one of the directions to be the opposite of the direction of the ball. That's called drag. So if you want to think you're driving in a car, you stick your hand out of the window, you feel that backward pull. That's called drag. And then the other one is whatever the other component is orthogonal to it in the up direction, and that's called lift. And air resistance is just the sum of those two things by definition. The lift comes in because this ball is spinning in this direction, and that's speeding up the air as it goes over the top, which by Bernoulli's principle creates a lift that pulls it up. And that's usually important because the ball stays up there a lot longer than it would otherwise. And you saw it. You saw that ball goes up when you'd expect it to go down. But you have to model this. You have to put numbers on this so you can incorporate it into your model. So this is a long, long story. This is basically fluid dynamics, the movement of fluids and their interaction with solids. Drag is caused by two main sources. There's the friction, which is what you're feeling on your hand, and there's also the pressure differences. So when a ball is going, there's a wake behind it that has much lower pressure than the air it's compressing right at its nose, and so that tends to pull it back also, and that's also a form of drag. So one of the great insights in understanding fluid flow, and in particular drag and lift, was the Reynolds number invented by Osborne Reynolds in the 19th century. And what he did is he found that this Reynolds number could take flows from a vast regime, things that are very different, like water going past this ocean freighter, big turbulent high momentum movements of water that would bang everything around and mix everything together, swirl, and honey pouring into a bowl here or into a spoon where it's very laminar and steady, slow sort of flow. So what makes these two things different? Well, he said just compute a number in the following way. Look at the density of the fluid, mass per unit volume. Look at the diameter of the system that you're studying. So not the whole ocean, but maybe the length of the boat, basically the area that's affected by the boat. Or here, roughly speaking, this pile of fluid here. You don't have to get the Reynolds number right. A factor of 10 is not bad. So you could take anything from the diameter of the spoon to the diameter of the stream as this diameter. And then the speed of the flow. So, well, we can, the speed of the boat, for example, or the speed of the water going by the boat if there's a large current, and here the slow speed by which the honey pours out of the jar, and then divide it by the viscosity. So viscosity maybe is not quite as familiar. Of course, we know that's a measure of how thick or thin the fluid is. High viscosity fluid is one like honey that flows slowly. Here gives you some numbers for fluid. For golf, we're interested in the viscosity of air. That's not zero, but it's a pretty small number. Water is also a pretty low viscosity fluid, but it's about 50 times more viscous than air. Blood is thicker than water, and that's true. It's twice as thick as water. Corn syrup is thicker than blood. That's not as popular, but it's also true. And honey, and of course you can't win a ketchup race because it's a high viscosity fluid. And pitch, so this is interesting. This is an experiment that is going on at the University of Queensland in Australia. It's in the Guinness Book of World Records for the longest running experiment. It was started in 1927. I think in 1926 they melted the pitch and put it into a funnel that had sealed at the bottom. They waited a year for it to reach ambient temperature, and they cut off the seal at the bottom and they let the pitch start dripping. 9 years later, a drop came out. And everywhere, somewhere between 9 years and 13 years, there's another drop. So the 9th drop fell, I think last year or the year before. And somehow their webcam was on the fritz that day, so nobody has ever seen a drop fall. But you can now watch it live on the web if you want. And they're expecting a drop to go. I think it's another 14 years they're expecting a drop. So. Okay, so you take that viscosity and you put it in the denominator. You get a dimensionless quantity, the Reynolds number. When it's big, you got turbulent fluid flow, fast, swirly mixing. When it's low, you got laminar fluid flow, slow, steady, orderly. So what about golf? Well, the density of air. Well, so we think of air as having almost no weight, but that's because we live in it. It's above us and below us. Cubic meter of air weighs a kilogram. A golf ball is about 4 centimeters in diameter, and we found that it goes into flight at 175 miles an hour, 80 meters a second, and there's a viscosity of air, and we can come out that the Reynolds number of flow of a golf ball in flight is 160,000. You can compare that to a butterfly, which is only 4,000, or a blue whale, which is 300,000. So a golf ball is a moderately turbulent sort of situation, but nowhere near what a blue whale creates, more than a butterfly's wing creates. Even a butterfly's wing creates small vortices at the end as things mix up. If you get down to really small, slow-moving things like bacteria, what does this mean that the Reynolds number is so small? It means to a bacteria swimming through water, it's like swimming through pitch. I mean, it is like going through a solid. It doesn't feel like a fluid to the bacteria. Okay, so now we get back to drag. Now we have the tool of the Reynolds number. By the way, the Reynolds number is crucial for many things. When they don't build airplanes using computers, they build them, and they used to build them completely using wind tunnels. Well, you can't do too much. There aren't too many wind tunnels that you can put something as big as a Boeing 747 in. You put a scale model of a Boeing 747, and you put something that's much smaller. Then you have to adjust all the other parameters, and what you do is you arrange so that the Reynolds number doesn't change. And then what happens in the wind tunnel tells you something about what's going to happen in your usage situation. Okay, getting back to measuring drag. So now go to the beginning of the 20th century. The Wright brothers had their first flight. So flying became big stuff now. Everyone wanted to learn about aerodynamics and how you could make flying a useful thing. So one guy who had a lot of money, time on his hands, and wanted to make a big impact was Gustav Eiffel. He had already built the Eiffel Tower, and he decided to now put his efforts into aerodynamics. And he decided to build an aerodynamics lab in the Eiffel Tower, because it was a great place for dropping things and see how fast they get and measuring drag on them. So he actually built the first wind tunnel on the grounds of the Eiffel Tower, and he built his laboratory high up in the Eiffel Tower. There it is. And he made a bunch of experiments. In 1912, he made a truly shocking discovery. And I will show it to you as explained by an MIT math professor in an old video, a guy named Asher Shapiro.
I suspend a 3-inch sphere at the end of the lever arm in the air jet. We're going to increase the airspeed and see what happens to the drag force. I'm going to start the motor now. Here we go.
So that's the speed of the
You see
wind.
that we have brought the speed up to about 75 miles per hour, while the drag force reads about 1.5 units on the scale. I'm now going to increase the wind speed to about 100 miles per hour. The wind speed, you see, is about 100 miles per hour, while the drag force has increased to something a little less than 2.5 units. Now I am going to increase the wind speed continuously, and I'd like you to observe what happens to the force on the scale. Here we go. Up, 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 but now it's going down, down, and up again, up, up. She's continuing to rise, continuing to rise. Now that was very puzzling, and it's not quite clear what happened, so I think we'd better repeat it.
We won't repeat it. But I hope you saw that this has kept going up, up, up. That's the speed. And this went up, 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 down, up. So that was called the drag crisis. And why should it happen? I mean, imagine your hands out of the window, you speed up the car, you expect to feel you're being pulled back more and more. All of a sudden, it's pulled back less. So that became Eiffel's paradox, and one wanted to explain it. It has huge impacts because it reduces drag. So your golf ball can go further, your plane can go further, and so forth. So here it is in a plot. We have the speed in miles per hour of some smooth sphere, or really what matters is not the speed, it's the speed and the diameter, also the viscosity and so forth. So the Reynolds number, this wouldn't change if I changed to a different sphere. The speed would change if I changed to a different sphere. It's the Reynolds number, but so at a speed of 80 miles an hour or a Reynolds number of 100, where here we're going up sort of quadratically, but then at somewhere between 200,000 and 250,000, we have this drag crisis and we drop down. And then we pick up quadratically again. And if you compare this quadratic to this one, the drag force has been reduced by a factor of 4. So it's a huge difference. So why is this? Well, the person who figured it out was this guy. So he's the hero of this part of the lecture, Ludwig Prandtl. So he was a mathematician, but really he was an interdisciplinary scientist who did experiments and did engineering as well. And he had started to work on understanding fluid flow before Eiffel made his paradox, discovered the paradox. And his big contribution as a young man was an understanding of boundary layers and boundary layer separation. So there's fluid coming in around this sphere, and because there's a viscosity of the fluid, it sticks to the sphere. So actually, if you were to go to the very, very thin layer right around the sphere, the fluid is not moving. It's compared to the sphere, it's just sticking to the sphere. But you get just a tiny bit off it, and it's flying by quickly. And he wanted to understand that and wanted to understand why this layer that it forms then separates and pulls away, because that creates this big low pressure wake, which has a huge effect on the fluid flow. So he went to the ICM in 1904, the most important math conference, and he published this paper. It's in the proceedings, which was sort of a founding paper of modern fluid dynamics. Some interesting stories about him. Felix Klein, who was one of the greatest mathematicians alive, was at the ICM. And as you know, Felix Klein was very interested in math education. And he was in charge of setting up a set of institutes to bring German higher educational system into the 20th century. And he heard Prandtl's talk, and he said, "You're the man, you should you're going to direct the new institute we're opening up in Göttingen." And that became the world center of fluid dynamics. Von Karman was there. He was Prandtl's student there. And then when Nazism started to rise, he came to the US and started the aerodynamics program in Caltech, and much of modern fluid dynamics came out of them. Another story about Prandtl, he was a nerd. There's a story that about 10 years after this, and he is now running the institute, doing very well, he went back to his thesis advisor, August Vogel, and he said, "Herr Dr. Professor, I'd like to come here to ask for the hand of your daughter." And Vogel was a little surprised because he didn't know anything had been going on. And he said, "Really? Which daughter?" And he said, "Oh, Herr Dr. Professor, I leave that up to you." So he got together with his wife and they decided the eldest Gertrude was the right one, and they lived happily ever after. This is the paper he presented to the International Congress on fluid motions with very small viscosity. And what you see here, well, so far we've seen algebraic equations, ordinary differential equations. Now you see partial differential equations. These upside-down triangles are gradients and Laplacians. So now we're coupling the change in time of the velocity of the fluid with its change over in the spatial directions, also coupled to the pressure and the density. And these are the famous Navier-Stokes equations, almost exactly like you would see them written today. And this is one of the greatest mathematical models of all time. It's very simple. It's not difficult to derive. And it's pretty much felt that it holds the key to almost all aspects of at least incompressible fluid motion. That if you could solve this exactly, you could use it to predict what the fluid would do, and then you could use it to start studying control and so forth. Unfortunately, you can't solve it exactly. In other words, you can't even decide whether it has solutions in all cases. If you do, you get $1 million from the Clay Institute. That's one of the Millennium Prize questions. So what Prandtl did was what a good mathematical modeler did. He simplified it. He made it worse in a way that wouldn't be much worse near the boundary layer that he was studying, but would be more amenable to analytic treatment. Of course, he didn't have computers, poor guy. So he created the Prandtl boundary layer equations, which are a simplification of the Navier-Stokes equations that happens in this very thin layer near the solid surface. This is the very thin layer. This is tiny, despite the way this says magnified. So this is a very tiny layer. And what it's showing is that the velocity of the fluid is 0 down at the surface. And then it increases more or less linearly as you go away from the surface until it reaches the speed of the ambient flow outside, and then it stays more or less constant. So now imagine we're applying this on a ball. So here's the air coming in. It hits against the nose of the ball and creates a high pressure zone. And then it goes over the top of the ball and it gets more rarefied as it spreads out. By Bernoulli's principle, then it's creating a lower pressure. That's what makes airplanes work. And then it goes around the backside and reforms to a high pressure zone again. So now imagine we're looking at basically this area here. That's this picture here. This is the very top of the ball. And so we have the fast, low pressure air here, and then which is here. And then behind it we have the slower, somewhat slower, high pressure air. So what Prandtl figured out from looking at his boundary layer equations is this high pressure here, well, that's going to push the air back. The air is rushing by. Well, it's not moving right at the surface, but here it's rushing by. And now there's this higher pressure, and that's going to push it back, so it won't rush as much. And at a certain point, it's going to actually force the air backwards against the prevailing flow. That's what you see here. And that's the point at which the boundary layer separates. So he's basically seeing down to a molecular level what's going on in this fluid, but not using a microscope, using mathematics. Nobody had a microscope that could see this. There's his picture. And here's an experiment that was done in 1988 to try to actually visualize it. So what do you have here? You have a fluid over a solid surface, and there's a wire here, very, very thin wire in the water, designed to hopefully not disturb the flow very much. And you put a little shock in it, it makes a bunch of bubbles, and then the bubbles start floating with the flow, and you're doing time-lapse photos. So you're making this picture, and you can see that that's what it had. It goes from 0, goes up linearly till it reaches a prevailing flow. But then they did it over a curved surface to try to see boundary layer separation. And you can see, really, he captured the story very, very exactly. It's really matched by the physical proceedings. Okay, so this was 1904. He had explained boundary layer separation. Then, 1912 or whenever it was, Eiffel discovers his paradox, the drag crisis, and Prandtl sets to work to try to explain it using his boundary layer theory. And here's what he came up with. It took him a while, but 2 years after it was discovered, he was able to explain the drag crisis. So remember, if you increase the speed of a flow, you increase its Reynolds number, and eventually at a certain level it becomes turbulent. That's true for any fluid flow. It's true for the flow in the boundary layer. So if the boundary layer flow, not right on the surface, but just a little bit up from it, gets fast enough, then the boundary layer itself will become turbulent. And that's what you see here. Here's a nice laminar boundary layer, and here's a turbulent boundary layer. Now so if you go a little faster, you get a turbulent boundary layer. So what does that do? Well, turbulence is mixing. So you start mixing the air around here. Well, you have really fast air off the surface, slow air right at the surface, and now you mix some of the fast air with the slow air, so you speed up the boundary layer. That happens when the boundary layer becomes turbulent, and for a smooth sphere, that's about Reynolds number 250,000. So the turbulence mixes air further from the boundary layer into the slow air near the boundary and speeds it up. So the air in the boundary layer, well, remember this picture over here, this famous picture. This air is getting pushed backwards, and that's what calls boundary layer separation. Now this air is moving forward. It can resist that pressure trying to push it backwards longer. So it goes longer until it separates. So the net result of this is once your boundary layer goes turbulent, it can resist boundary layer separation till further downwind on the ball, and therefore that pressure wake at the end is smaller, and the pressure wake is low pressure causing drag, so you reduce drag. It's a pretty complicated system of reasoning. That's what he came up with. And here's the sort of proof in experiment. This is an experiment that was done later, but actually Prandtl did basically this experiment. This is a recreation of his experiment. Here is a smooth sphere, and here's the flow, and there's the boundary layer separating, and here's this big low pressure wake causing drag. Then to test whether turbulence changed the situation, he kept the speed the same, but he put a little tripwire around the ball. So that little tripwire causes turbulence. And if you, next time you're sitting on a window seat near a wing, look, you'll see there are little things there that are designed to create turbulence to delay boundary layer separation. So this tripwire, and what you see is the boundary layer separation has now moved down to here, and we have a much smaller trailing wake, and therefore less drag. Okay, so story is we now understand why at Reynolds number 250,000 the drag goes down, because when turbulence commences. The only problem is that's 205 miles an hour for a golf ball, and golf balls don't go 205 miles an hour. They go about 175 miles an hour if you're really good. So why does this make any difference to golfers? Well, that's somewhat explained by another video of Asher.
We're ready to begin the experiment now with a roughened ball near me.
Roughened ball, smooth ball. And they're in balance, so you can see which has more force.
You see that the speed begins at 30 miles per hour, and the deflection of the balance beam indicates that the smooth ball has less drag, as you might possibly expect. Now I'm going to increase the speed, and as I do, the beam deflects still further, but the smooth ball has less drag all the time as the speed goes up to 75 miles per hour, 100 miles per hour, approaching 125, but there she turns over, and now you see that the smooth ball has more drag, indicating some sort of reversal in the flow pattern.
Okay, so did you get that? So actually, it's the tripwire trick. It's the thing that Prandtl discovered. You put a little tripwire in there to force turbulence, and you lower the wake behind, and therefore you lower the drag. Instead of the tripwire, they roughened the ball. They sanded it in some way. And that can have the same effect. So it's sort of paradoxical. You'd think that would increase the friction, which it does, which increases some drag, but it also changes the flow, which decreases the drag even more at certain speeds. So when you do that, a suitably rough ball will experience a drag crisis way down to Reynolds number 50,000. And that's well within the range of even a amateur golfer. And therefore your ball will go much, much further because the drag has been reduced. And in fact, the difference between hitting a smooth golf ball and a roughened golf ball is about double. So it's huge. Well, golfers had discovered this before Prandtl. What happened was, in the early days of golf balls were made by sewing leather into an inside-out sphere, stuffing it with wet feathers, and sewing it back up again. It was only the very rich could play because it took a man a day to make a ball. And then with British colonization, they got gutta percha rubber imported, and they were able to make nice, smooth rubber balls that anybody could afford. And then the golfers found they didn't go as far. And then they found, well, when they got old, they went pretty far. So then they started hitting them with hammers as soon as they got them, and this and that. And they started getting all these different things here. And it's continued into the present. So it's finally evolved into the modern golf ball. And there are something like 1,000 patents for different possible patterns of dimples to make the ball that will go the furthest. What do you want? Do you want round dimples or hexagonal dimples or triangular dimples? How deep should they be? Should they all be the same? How should they be distributed and so forth? That's in fact a huge space to explore. You'll never be able to do it by trial and error. And so there's still going on the elusive search for the best dimple pattern. That one is a recent edition that was front page news in the New York Times. And so this is a question of optimization. So now we have a mathematical model, now we can play with the parameters of it and try to make it optimal. And this has been very big in competitive sailing. This is the America's Cup boat. So the boats are now optimized so they don't even look like boats, but they're very, very fast. I'll let you read that one. So now to optimize dimples, well, you're not going to be able to do this through mathematical analysis. Even a Prandtl couldn't do that. But we were able to use the models, say Navier-Stokes model, to try to do the simulation. And while we can't solve it analytically, we can solve it very accurately on a computer. So that becomes computational science. And this is sort of state of the art. This was a group around Kevin Squires. These speeds are somewhat below professionally hit golf ball. They're not quite up. It's more turbulent. A real golf ball would be more turbulent and harder to simulate. And in addition, the dimple pattern is pretty realistic, but the ball is not spinning, which is a huge thing in golf, but also makes it much, much harder to simulate. But nonetheless, this is a very impressive computation, and you can see a lot. So this is produced by that group. So this is one way to visualize the flow past the golf ball. And you'll see we'll keep going in and in and in and looking at finer and finer levels. Okay. So you can see that the flow is very definitely affected by the dimples. And we can try to follow little blobs of fluid and see exactly what's happening. So we're going to go in even closer and look at just a few dimples. Closer, please. Okay, so you can see the boundary layer actually separates because the dimple acts as a tripwire, but it reattaches. There's a reattachment from the dimple. And you can look at it down at the level of a single dimple and try to see what's going on. So you have incredible powers by a good, well-made computation to understand what's going on. And I just want to close. I want to mention how is it that we can produce a computation like that these days. So the first one is from a paper by Jules Charnay, Ragnar Fjortov, and John von Neumann. Von Neumann was one of the inventors of the stored program computer, and he wanted to use it to do real science. And so he had his ENIAC computer, and he said, well, a problem that we could work on is weather prediction and climate. Weather prediction particularly. And so what he did is he put down a grid, took North America, put down a grid of points. At each point he represented the weather by its temperature, velocity of the wind, and the pressure, I think, and wrote down equations, simpler than Navier-Stokes, but also bringing in some other aspects called the geostrophic equations. He wrote down some equations that coupled all these variables at these 270 grid points he had, and then he fed those equations to the ENIAC computer to solve. By using 270 grid points, he had pretty much maxed out his computer power, and it took him about 24 hours of computation time to do a 24-hour forecast. So he couldn't go much more with that hardware. Now compare that to the computation I showed you. They used 1.2 billion grid points in order to get enough down in an individual dimple that you could see what was going on. So how is it that state-of-the-art in 60 years went from here to here? Well, of course, one obvious answer is we have better computers than we had then. That's the Moore's law. Every year and a half or so, it's doubling the speed. And if you figure it out over a 35-year period, I figured it out for this problem. Over a 35-year period, Moore's law caused a speed up of what we could do then to now, a factor of 10 million. That's this line here. So if we go back 35 years, if it took that amount of time then, it took 10 to the 7th times. It took 1 over 10 to the 7th time. The speed was 10 to the 7th times more due to hardware improvements. But at the same time, we don't use the same algorithms von Neumann used. He used Gaussian elimination to solve the equations. A little bit later, people started using the Gauss-Seidel iterative laws, and then the work of David Young in the 60s, they went to optimal successive over-relaxation, and then with the invention of the conjugate gradient method by Hestenes and Stiefel, they got a big speed up on that, and then with the invention of the multigrid method, and finally full multigrid. So this is a method that's currently being developed, but it's probably been used quite a bit in the last 10 years. That accounts for a problem the size of the one we were talking about, a speed up of 100 billion instead of 10 million. So the speed up from smart algorithms is much more of a factor. And of course, what allows us to do it is both of these are being put to use. So I'll end with this. It's a quote from a presidential report that just emphasizes how this computational simulation is now really fully standing third pillar of the scientific enterprise alongside theory and experiment. And so the message I wanted you to take away from this, you can do an awful lot by an artful mathematical model, mathematical analysis using whatever mathematics is appropriate, and smart computational simulation. Thank you.